Welcome back to How to Program, and just a reminder that this show is best viewed in order, and if you need to start back up at the first episode, if this is your first time seeing our channel or our videos, the link to the first episode should be below in the description, and you should click that and just go through in sequence. It'll make a lot more sense. Now this is going to be episode 11, and we're going to talk about higher level languages, and the first thing we're going to do is we're going to define what a language is. So a language is the method of human communication, either spoken or written, consisting of the use of words in a structured and established way. Or, in computer programming, it's a system of symbols and rules for writing programs in a computer. So, I just want to point out there's a few elements here. You know, we're saying that it's a way of communicating something. Like we want to give it some meaning or some direction when we use a language. Just like I'm using English right now to explain this to you, it has some meaning and some direction or some statement that it's saying. And then it has some rules about the structure, like the words go in a certain order or they go in a certain sequence, and then you can understand the concept in that way. Well, just in the same way the computer has rules. It has what's called grammar, and grammar is just a system and structure of a language or of languages in general. It's a set of rules about how the words and the symbols fit together in a language to form statements or sentences that can be understood by others. Like, otherwise it would just be gibberish, like you wouldn't understand me. Now, there is grammar in programming languages, and it's just the same thing. It's just a set of rules about the order of the words and the symbols in the language and what those words and symbols tell the computer to do. So you will hear sometimes about, oh, this language has a different grammar. It just means like the set of symbols and the set of rules to write in that language to mean the same thing is just different. Like if I want to do something in one language and I want to do it in another, it's written in different ways. So next, let's review what assembly or machine language is. And very early on, I explained that assembly or machine language is the language that the processor actually speaks. This is the set of instructions the processor understands, and it is the only set of instructions that the processor understands. Now, this is also called an instruction set because it's a list of all the possible instructions that can be directly given to a processor. And there's different instruction sets or different types of machine language, and these depend on who the manufacturer of the processor is and what they want the processor to do. Like Intel and AMD processors have a common set of basic instructions that are called x86, but on top of that, they have a special set of instructions that work only on their own processors. For example, AMD 64 for AMD processors and Intel 64 for Intel processors. Now, the 64 is there because 64 bits is the smallest unit of memory that those processors will deal with. And that's why they put 64 in there. Processors that run on your phone, like on a smartphone or something like that, they need to use less power so that the battery can last longer. And so they use a different set of instructions called ARM, which stands for Advanced Reduced Instruction Set Computer Machines. And this is the R, expands out to another acronym in the ARM thing here. And these are just, the manufacturer might be something like Qualcomm is the name of the company that manufactures a lot of these smartphone chips, and they use ARM instruction sets. Now, very few developers write assembly these days. If you remember the early lessons we did, it's kind of tedious to write assembly. Like line by line, we have to, manage the memory, manage, like basically every minor detail of writing a program. And it is considered to be the lowest level of programming language because this is what the processor actually runs. So the lowest level means that it's not being translated into anything else before the processor executes it. You literally have instructions in ASCII format in binary that go from the memory into the processor, and the processor decodes the ASCII representation of those instructions and executes the instructions, basically, doing addition, subtraction, moving data around, copying things, etc., comparing things. So because assembly is hard and tedious to write, programmers developed languages that were easier to write, and because those languages cannot be directly executed on the processor they run on, they must ultimately be translated into machine language or assembly for the processor they will run on. Now there's there's another thing here to consider is what's called the operating system, and you'll be very familiar with this. This is a set of basic programs and code that manages the hardware of the computer. Like you have a processor which can run code, but then you have other things on your computer that also supply services in order for the whole thing to run. Like you have a hard drive, and that has its own set of instructions in order to be able to read data off of the hard drive, you know, from files and so on, or managed files like a file system where you have folders and files and things like that. Like that would be part of the operating system. If you have a network card or Wi-Fi, that needs to be managed as well to make connections on the network. So all those basic features, displaying things on the screen, etc., are part of the operating system. And each operating system is written differently. So generally programs have to be able to, they're written in a way that they can run on a specific operating system, and they can't run on another one without being rewritten or without taking into account the fact that they may be able to run on multiple different operating systems. The most common operating systems are Linux, Mac OS, and Windows. Mac OS and Windows being the ones that users use the most, and Linux is the one that we use the most when we're developing servers or writing code that does not have a user interface. Although you can have a user interface, and it's actually very good on some of these versions of Linux, and use that as your primary operating system, but not that many people do it. Okay, so we talked about translation. Ultimately, like I said, all the code that runs on a processor is assembly. Nothing else can run on the processor, which means that if you write in a different language than assembly, that code has to be translated into potentially several different languages as it progresses down closer and closer to assembly. And we usually, because there might be different levels of translation, we consider this that these languages sit at different levels. So you could imagine that there's, you know, you, the programmer, at the top, and then you're writing in your high-level language, which we'll see some of the names of those languages in a minute. And then this may be translated into what's called an intermediate language, sometimes also called an intermediate representation, which is just another language that just is closer to assembly, but is not quite assembly, that can be optimized a little bit easier by the computer. We'll see a little bit about this in a minute. And then eventually your program is translated into assembly instructions that go directly to the processor so they can run. Now, the translation can happen in two ways. You write your code in a high-level language, and then you can decide to have this translated, well, depending on the language that you're using, I will say. Your code can be translated while your program is running or before your program starts running. If your program is going to be translating the code you wrote while the program is running, this is called interpreting the language, and it's done while the program is running by what's called an interpreter. The interpreter is just another program, and that program takes your code, and it basically reads it kind of line by line, you could say, right? And then executes it line by line, right? Or statement, instruction by instruction, you know, and it runs that and interprets the code at the same time. So this can be, this tends to be slower. In general, it is slower than doing the next thing, which is to translate the entire code before the program runs and then running it. So this is called compiling, and it's done by the programmer. So you sit there and you're going to use a program called a compiler, and a compiler is just a program that translates your high-level code directly into assembly. And then that compiler is going to look over your entire code, and it's going to translate it, and then it will give you what's called an executable file, which is basically a file containing all the assembly language instructions that are your program. Right, so conceptually, you have some code in your high-level language on the left here, and for interpreting, there's an interpreter. This turns the code into assembly as the program is running, and then it sends these assembly instructions to the CPU for you, and it does this as your program is running. So when it starts, nothing is translated, and then it translates the first line, then it sends it to the CPU, then it translates the next line, then sends it to the CPU, and so on, right? Now, there are some advantages to interpreting. It does not require compilation before running your program. Compilation can be lengthy sometimes. It can be several minutes or even hours on very large projects. So as a result, this slows down your developing of code, because if you have to make a change and then you have to sit there for an hour before you can test your change, this can be very long. And I've actually worked on projects at Facebook where the compilation time for some of the server-side things that were being run, the compilation time could take up to an hour for compiling something from scratch. So this is a real issue, and having a language that is interpreted completely removes this compilation step and just lets you basically hit refresh on the page, if you will, or just start the program up again and immediately run it without having to wait for it to compile. Interpreted languages can use different optimization tricks than compiled code to make your code run faster, because the interpreter is running while your program is running and is translating your program as it's running. It can learn things about your program, like which code tends to run the most. Like you will have sections of code that is kind of your main code, what we call the hot code, like the code that runs the most. And it can like optimize the crap out of that because it sees that's the code that's the most important to optimize. Whereas a compiler doesn't have any information about how your code is running and can't make those decisions. It does generally tend to be slower than compiled code, but this is constantly changing because interpreters and compilers are improving, and it's kind of a race between the two, really. So this is not really always true anymore. There's some competitions between those two, and it's still, this is kind of an ongoing battle between interpreted languages and compiled languages, right, as to who can run the fastest. The same code for interpreted languages usually can run on any operating system without needing to rewrite or change your own code. Now, that doesn't mean that the interpreter doesn't change. Like someone will have to write an interpreter for every operating system, but your code will not need to change, which is a cool part of this. Like you can have a program written once and you can run it on Windows and Linux and Mac, and it will run the same in all three, basically. Now, let's look at compilation. So compilation takes your code here at the top on the left, and then it goes through the compiler. This turns it into assembly and writes that to a file. It doesn't execute it. Just writes it to a file. When you want to run your program later, you take that file and you run it, meaning you send those instructions to the CPU, and then it starts to go through. So that's different. The advantages of compilation, of course, are that you can make use of specific instructions for a given processor and really squeeze out a lot of performance, because the compilers are generally more on the cutting edge of working with Intel and AMD on, improving the speed of processing, for example. Compilation also detects some errors that you made in typing your code. For example, if you forgot some symbols or something and then the code doesn't actually make sense to the computer, it will detect that and it will not compile. It will just throw an error and say, hey, you have an error in your code you need to fix before I can actually compile this because I don't understand this, right? The interpreter will not do that until it hits that line of code. Like your program will probably run with the interpreter until that line that has the error gets run or tries to get run, and then the interpreter will say, oh, well, now I can't. Now I have an error. So it can detect bugs ahead of time. This can be useful. And you usually have a greater degree of control over exactly what the processor and other input and output devices will do precisely in compiled languages that sometimes can't be done within interpreted languages, just because interpreted languages tend to omit a lot of the finer details because they are somewhat hiding a lot of the details so that your program can run on different OSs, for example, which is something that often interpreters do. So they will give you access to the file systems and like to write files, for example, but they won't give you necessarily the very precise control and access that you need for the particular operating system that you're running on or something like that. Okay, now there are two more big classes of ways the code can get turned from high-level language into assembly, and these combine the two earlier approaches I was talking about of compilation and interpreting together during program execution, mixes them. This is confusing, but it will make sense in the example. Because some very popular languages of today use these approaches, including a language we're going to cover later, it's good to know what these are because we'll talk about them. So the first one is called a virtual machine. Now, what happens with a virtual machine is that your code gets compiled into an intermediate language, so a language in the middle. It's not quite assembly, but it's not a higher level language anymore. Like you wouldn't want to write this because it's kind of tedious, but it's not assembly. It can't run directly on the processor. This is also sometimes called an intermediate representation or bytecode. You then use a second program called a virtual machine. This virtual machine it's like a virtual CPU, basically. It understands and can run bytecode. And what it does is that when it reads the bytecode instructions, it then issues assembly commands to the CPU that match those bytecode instructions. So the advantage of this is that if you have a new operating system or a processor that comes out, you don't need to recompile your code to match that operating system or CPU. You just need to update the virtual machine to be able to run on that OS or CPU, because your bytecode, your compiled version, which is bytecode at this point, is not assembly anymore, can run on any virtual machine that does this. So a very popular language which uses this approach is called Java, and one of the big features that Java has is that you can compile your code once and then deploy it on any operating system. And you still get a lot of performance like a compiled language would, because it's compiled ahead of time. So you get a bit of the benefit of kind of both approaches, right? Now, another thing that happens is that some interpreters, so now going to interpreted code, some interpreters realize that in order to speed up running of code, they could compile sections of code on the fly and then save the compiled section. Next time that same section of code needs to be run, the interpreter already has compiled that version, so it just runs that. This is called just-in-time or JIT compilation. Now, for example, browsers run a language called JavaScript, which makes the page sort of interactive. Like basically every website at this point uses JavaScript. And when code runs in JavaScript, if a particular piece of code is running over and over and over again, right, well, JavaScript will sort of realize that, oh, wow, these 4 lines of code, they're the ones running like 2,000 times a second or something, right? And it will go, okay, let me pause for a second. We're gonna waste some time here. I'm just gonna compile this. Or it will even do this on the side at the same time as your program is running. And then it will save that compiled version, and the next time it comes, it just goes, oh, lines 4 to 6. Yep, I have a compiled version of that, so let's just go plug that in and run that, right? And it's just another way of translating code. Like, it can do more optimizations that way. Anyway, it's just good to know what it is. The details, of course, are a little more complicated, but we're not there yet. Okay, now there's 2 more features that languages have that I think are important to know when you want to pick a language or when you want to see which language is going to work best for your particular project. And let me talk about them a little bit now. The first one is called managing memory or memory management. And this can be difficult because normally what you do is you request memory from the computer to store data, and that's very easy. But when you're done using that memory, you need to tell the computer that you're done so that that memory slot, that piece of memory that you're using can just be freed up for reuse by your program or by other programs later. If you forget to free this memory slot, this basically means your program's memory will leak. That's called a leak, memory leak. And that means that you're not giving up the memory that you're no longer using. So now you're just growing and growing and growing in size of memory until the operating system goes, hey buddy, like you're using way too much memory, so I'm just going to kill you because you're about to, use up all the memory available for this computer, and I can't have that. And the operating system kind of acts as a cop there, just kind of killing your program at that point, right? So now some computer languages require you to deal with memory freeing yourself. You have to keep track of which memory slots you reserved or you said you wanted to use, and then when you're done with them, then you have to free them. This is called unmanaged memory because the computer is not managing the memory for you and you have to do it yourself. And it can be kind of hard and cause a lot of bugs if you're not careful or you don't know what you're doing. Now, on the other hand, certain languages will take care of freeing up the memory for you when it's no longer being used. They keep track for you of which memory you requested, and then they will free it up when they can see that you're not using it anymore. And there's ways for them to see that you're not using it anymore, that they know you're not using it anymore. Memory leaks can still occur in these languages, but they tend to be a lot less frequent, and they are a lot easier to identify and fix because this whole tracking of memory system is already in place to know what piece of memory is using what other piece of memory and that kind of thing. Or what piece of your program is using what piece of memory, rather. Now, languages which do this for you, so they manage the memory for you, are called, they're referred to as having managed memory, right? They manage freeing the memory for you. Now, Java and JavaScript, for example, are 2 languages. And the name Java, by the way, I know is in common, but they have nothing to do with each other. So don't get confused and think that Java and JavaScript are similar. They are not. They are completely different languages. It was a marketing trick to try to call them the same thing. But anyway, so Java and JavaScript are two different languages, but they both manage the memory freeing for you. A language like C, for example, does not. Another language called Objective-C, which you can use to write iOS apps, has an option for you so you can turn it on and it will manage the memory for you. So you can see that it's not always, you know, all black and white. Sometimes things can be turned on, for example. Another big thing, so this is the second other big thing that I wanted to talk about that makes languages different from each other, is we saw earlier there's many types of things you can store in memory. Like you can store integers, floats, booleans, strings. Certain languages require you to always specify the precise type you want to use when you're creating a variable, like a slot in memory that you're going to use is called a variable. And if the language has you specify that, then you can't change that type. So you say, I want a piece of memory to store a string. And then that piece of memory is now always going to be storing a string until the end of your program running, and you can't change that type. So that's called statically typed languages. The type of the variable is static. It can't move or it can't be changed once you set it. It doesn't mean that you can't copy the data and then change its format. Like, you know, if you have a piece of string and you say, well, I'll turn that into an integer because I know that there's a number in there, you can do that, but you can't change the original variable. You know, you have to create a new variable to do that. So that's called statically typed languages. Now, on the other hand, you have certain languages that let you omit specifying the type of your data and figures it out for you. It will use the data type that seems to fit best, and then that can be changed later in various ways while keeping the same variable. Like you can use the same slot in memory, but then you can change dynamically. So dynamically means, you know, on the fly, like while it's running, right? So these are dynamically typed languages because the type of the variables is dynamic. It can change. It's not set in stone. Now, I made a big table here. Don't get frightened. This is actually very simple. These are the four. These are the three things we talked about here. The type of translation, so is the language compiled, interpreted, virtual machine, or otherwise? Is the memory managed for you or not? And is the typing static typing or dynamic typing? And as you can see, there's a lot of options, you know, and I put these languages in date order of when they were created, so you can kind of see, right? Some of these languages are fairly old at this point. They're like 40 plus years old. And some of them are very recent, like Go, for example, is Google's language, right? And it's actually a compiled language, right? Which is, I think, one of the more recent languages created that are compiled, because you can see in the list, like all these major languages, up until recently, they were all being interpreted or VM languages that were being created, right? But Go is a compiled language. So anyway, these are some of the ones that exist. We'll be dealing mostly with JavaScript and Java. We'll start with JavaScript and then we'll move on to Java later, because I think they offer, if you know how to write, you're going to need to know how to write JavaScript anyways if you want to do anything with the web. And Java is a very powerful language that has many uses, and it looks very similar to other languages. And so moving from Java to a different language is actually very easy once you know Java, because things don't change very much. The code looks very similar. So those are the two languages we'll use. But as you can see, there's many other languages that you could use, right? Now, the next lesson, we're actually going to start with JavaScript. So we're going to start writing our first program, and we're just going to go over some basic keywords and how to do things in JavaScript. So see you then. And you can also like our Facebook page to get updates as soon as the episodes come out, and I really recommend you do that. And if you really like our channel, you can also like the video, comment, and subscribe, and let us know that you like it. All right, we'll see you next time.